Okay, well, we'll take a look at. I have one more notebook. This is on miscellaneous tasks that you might want to do as you're creating a model of some kind. And then next week, during week 9, we'll do SQL stuff. So you'll get your intro on Monday, and then if you come on Wednesday, and I have a feeling Wednesday, if this is Friday of this week, I don't know what Wednesday of next week will look like. So, if you're here, I'll do more SQL stuff, okay? All right. So these are just some useful miscellaneous tasks that you can do using scikit-learn within Python, and they're quite handy, okay? So one of these things is feature engineering, okay? So feature engineering is kind of the idea of taking some variable, okay, or some aspect of the data that you have, and then creating either new variables or doing something with it so that, it becomes, because the way scikit-learn works is that it takes matrices and it operates on the matrices, right? So your x variables is when you do model fit, it's always model fit x comma y, and x is some kind of matrix of values. And so if you've got say categorical variables, you have to turn it into numeric values that scikit-learn can handle. Okay. So unlike R, okay, R has this thing where you can take a factor, and it basically assigns each thing to a value. So for example, if you had let's say color was one of the variables, right? And you've got red, blue, and yellow, okay? In R, it might do red is 1, blue is 2, and yellow is 3. You get like the levels variable, and it assigns each level an integer, okay? Scikit-learn will not like that, okay? If scikit-learn sees 1, 2, 3, it's going to think these are numeric values 1, 2, 3, meaning 3 is bigger than 2, and 2 is bigger than 1. 3 is 3 times as big as 1, and 1.5 times as big as 2, okay? Which makes sense if they're numbers, but it doesn't make sense if they actually represent colors, like red, blue, and yellow. Yellow is not, it doesn't make sense to compare colors. Yellow is not bigger or greater than or less than blue or anything like that. So scikit-learn does dummy encoding, or it calls it one-hot encoding. And basically, you're going to get, if you have red, blue, and yellow, each category gets a column. So you're going to have a column for red, a column for blue, and a column for yellow. And then, and for values that are red, it's going to get 1 in the red column, 0 for blue, 0 for yellow. If it's blue, it's going to get 1 in the blue column, and 0 for red, 0 for yellow. And if it's yellow, it'll be 1 in the yellow column, 0 for red, 0 for blue. Things like that, okay? So we can do that, okay? And so for the notebook that I'm running, okay, is going to use this data set called Titanic_training, right? And it's from the Titanic disaster, and we're gonna look at some of these variables, okay? So if I import this, all right, each row represents a person, okay? And we're going to it comes in with information. This person was Mr. Owen Harris, and Owen Harris Brond, I guess, okay? And he died in the, he was a third-class passenger, and he died. He was 22 years old, okay? And then this next person was Mrs. John Bradley Cummings. She was 38 and she survived. She was a first-class passenger. Okay, and so we're going to go through and we are going to use the one hot encoder. Okay, so we initialize one hot encoder, and we imported from pre-processing one hot encoder. Okay, so we're going to do one hot encoder. I'm going to say set sparse equals false, and we can look up the help file to see exactly what that means. All right, and then I'm going to go ahead and run the one hot encoder on the column Titanic sex. Okay, so right now sex has male and female, and so we do the encoder.fit. Okay, so it's going to run on this. Okay, and that returns one hot encoder, and then we'll go ahead and we will run encoder.transform. Okay, so it's a little bit different. Rather than fit and predict for things that are going to engineer features, we do fit and then transform. Okay, and so we can see what it has done is it has taken this column, which has categorical values like male and female, and the male gets encoded as 0, 1, and female gets encoded as 1, 0. Okay, so this first column represents female, yes or no. The second column represents male, yes or no. Okay. You can do the fit and transform in one step. Okay. So these a lot of these encoders will have the command fit transform. Okay. So it'll fit and then run the transform. You don't have to do it as separate steps. Whereas generally for all of the other models, you do model.fit, model.transform, model.predict. Here you can do a fit transform in one step, and we're going to get the exact same results as well. Okay. And if you want, you can ask, okay, well, what do these columns represent? All right. So once you do this, it'll say, okay, the first column represents female, and the other column represents male. Right. All right. And so here we can take this, and what we want to do is we want to basically modify our data frame so that the sex column gets transformed and that data is available. And so I'm going to just do pandas.dataframe, okay? And I'm going to do take the fit transform, okay? And then we're going to basically just kind of make it into a data frame here. Okay, so I just take kind of this matrix results and put it into a data frame. Here's another thing where I've applied it to passenger class. Passenger class is I think it's got 1, 2, 3. Okay, but again, the problem with having 1, 2, 3 is that we don't want Python to think these are numbers. Okay, it might be first class, second class, third class, but we don't want Python to say 3 is a number that's 1.5 times bigger than 2 and 3 times bigger than 1. Okay, so we also want to transform those into categorical variables. So I've done fit transform to passenger class, and we get this, and again, this represents kind of 1, 2, 3. If you want, you can do both of these things at the same time. So we're going to do passenger class and sex. Okay. All right, and I'm going to go ahead and I'm going to just subset this to just take a look at those two columns, passenger class and sex, and I'm going to drop any missing values here. Okay, and so here we've got third class passenger who's male, a first class passenger who's female, third class passenger who's female, and so whatever, right? So this has 891 rows, 2 columns. And I'm going to go ahead and do one hot encoder. Categories will be auto, and we're going to go ahead and do this. Okay, so we get results.shape, and we can see it automatically figured this out and does 891 rows, 5 columns. So P class turned into 3 columns, sex got turned into 2 columns, And if we kind of look at the first row, we can see if these represent first, second, and third class, our first passenger, who's a third class male, will go get a 1 for the third class column and a 1 for the male column. Likewise, right? And then I can kind of take this and I can apply it to the one-hot encoder as well. Okay, next I get 001, 01, and et cetera, et cetera, et cetera. Okay, let me sparse. If you have sparse true, the results come back as a sparse matrix. Let me just kind of show you the results here, which is I'm going to call this results 2 encoder 2. I guess that's fine. Okay. And then there's also an option called drop. Okay, and you can do drop first. So actually, let me do, I'm going to leave sparse as false, and I'm going to do drop equals, whoops, we'll do first. All right. Did I type this in wrong? Oh, lowercase first. Oh, this is why. Okay, so that's what a sparse matrix does. Okay. All right, so when you do drop first, what happens is that the columns 1, 2, 3 will get reduced to 2 columns, okay? And columns male, female will get reduced to 1 column, right? And so basically, if you know the values of columns 2 and 3, you can infer the value of the first column, right? Because only one thing is can be a 1. So this is useful if you're going to do something like linear regression. If you do linear regression, these 3 columns are collinear, right? Like you can derive the last column based on the other columns. So that's going to create problems. So so if we know these 2 columns, so we drop the first column and we just keep columns 2 and 3. And so this will be a third class passenger. We see 0, 0, which means it's a first class passenger, okay? We see 0, 1, so that's a third class passenger. A second class passenger would have 1, 0, okay? And then similarly, by dropping the first column for sex, we get female and male. We're just keeping the column for male, and we can infer who was female because those will be the ones who are 0 for male, okay? So that can be a useful thing as well. Let me just do this. Okay, and let me just show you what happens when you do sparse equals true. It's the results. Okay, so wait, is this what I wanted? Oh, okay. Yeah, the sparse matrix will tell you the coordinates of what is a 1 and what's a 0. Okay, so if we go back to this, okay, this one has a 1 in the 0, 2 position and a 1 in the 0, 4 position. Okay, and it has a 1 in the 1, 0 position. So if we call these columns, maybe I should look at this, right? So this coordinate is 0, 2, this is 0, 4, and this coordinate is 1, 0, and 1, 3, okay? And it lists off those positions. So it basically lists off the positions 0, 2, 0, 4, 1, 0, 1, 3, and those are the ones that have a value of 1, okay? So that's what sparse equals true does. So this will drops the column for first class because it can be inferred from the other two columns. Drops the column for female because it can be inferred from the column for male. And this lists the coordinates in the matrix that have a 1. Okay, and so depending on how you are processing your information, you know, it can be useful to do to have a sparse thing. But in general, if you're going to just kind of plug things into model.fit, model predict, I think sparse false is going to be preferred. All right. I hesitate to do this. This is a useful thing, but also a dangerous thing. Okay, and you really want to think before you impute missing data. You really want to think if it's appropriate to do such a thing. Okay, and you know there's more complicated ways for handling missing data, but we're going to go ahead and just kind of look at this. All right. So sometimes you have a matrix and there's going to be missing values in it, right? So I've got an X and I've got a Y, and if you want to do linear regression, you can really only fit a model if the row is complete. So either you have to throw away the rows where you have a missing value, or you have to plug something in, okay? Now, what value you plug in, this is a difficult thing to decide, okay? So probably the most common strategies are, or because they are the easiest, is plug in the mean and plug in a constant, okay? Those are the easiest ones, but you really got to think if it's appropriate to do, okay? Because if you plug in the mean for everybody, you're basically saying, for this person, we don't know this value, so we're going to just assume they are average on this thing, which maybe it makes sense, but maybe it doesn't, right? And if you think about it, maybe you can do it, but maybe not, right? And there's different things that you might want to consider that just make things up, right? So let's say you've collected information about people. You collected, you know, their sex, their height, their weight, whatever, right? Let's say their person's height is missing, okay? If you just say, all right, anybody who has missing height, we're going to plug in average. You know, the average height of everyone's probably around 5'7", okay? But does that make sense, right? If the person is male, there's a higher probability that they're going to be taller than 5'7". If the person is female, there's a higher probability that the person is going to be shorter than 5'7". So does it make sense to plug in 5'7" for their height? And maybe not, right? You might want to partition your data and say, well, because we know this person is male, we're going to plug in the average for the males. And that'll be like 5'9.5" or 5'10" or something. And we can say, because we know this person is female, we're going to plug in the average for females, which might be, you know, 5'4" or something like that. Okay? But then again, what you're effectively saying is, because this person is female, we're going to assume their height is 5'4", which again may or may not make sense, right? You might know other information about the person, and that might, you know, you might want to take that into account. But then now it's becoming like a double prediction problem, right? Like there's some response variable that you're trying to predict, and you're saying this variable gets plugged in and stuff, right? So I don't know. The easiest strategy is, yeah, just plug in the mean or just plug in a constant. But I would say not always the best, okay? Right? But you can have the imputer function, okay? So you have, there's a whole bunch of imputing things, and I don't have the time or knowledge to explain all of these things, okay? But you can always go to the documentation, right? And there's a whole section, 5.4, on imputation of missing values, right? And there's the multivariate feature imputation, which basically takes into account other variables to try to figure out what value it should plug in, okay? And you'll definitely want to read up on it before you do such a thing, right? But the simple imputer is called the simple imputer because it uses the simple strategy, right? Of do I plug in the mean, the median, or the most frequent value, all right? So these are just very, very simple strategies, or a constant. And so you can just say, so the simple imputer doesn't take into account anyone's other variables, and they just say, all right, we're just going to plug in the mean or the median or the mode if it's a categorical thing or something like that, or some constant, right? So so you can do that. You can just do, you just import simple imputer, okay? And then you initialize it. And then you do the imputer imp.fit transform. Okay, so much like these other tools, we're going to kind of be filling in the things. So let's look at x. So here's x, and if I do fit transform, okay, it says, all right, what do we have here? We got 3, 3, 4, and 8. Okay, so that is 12, 15, 18. Okay, 18 divided by 4 is 4.5. So it takes the column and it says, you know, the average of the other things, the mean of the other values was 4.5. So we're going to do this, right? Here we've got 0, 7, 5, and 8. Okay, 0 plus 7 plus 5 plus 8 is 15. Is 20. Okay, 20 divided by 4 is 5, and so it plugs in a 5 for the missing value. Okay. So it's a very simple thing, and it does it in one step, okay? And I mean, of course, we could do this ourselves manually, right? We could do NP and then do mean axis equals 1, and then fill in the missing values with those column means. But the simple imputer will do it for you very quickly, okay? Or if you want, you can just fill in a constant value, right? So you can say, I want to put in negative 99 or something, and you get something like that, right? All right, and then now that we have the imputed values, then you can plug it into linear regression, right? But again, you want to sit and think if this is the right thing to do, right? So maybe, maybe not. It's always hard. It's always hard. We're always, as statisticians doing data analysis, we always have to make assumptions, right? And somebody, your boss, hopefully, is aware enough to know to ask, what assumptions did you make, and question your decisions. And this will make you a better statistician, better data analysis analyst when you are able to defend your decisions, okay? When you do your presentations during 10th week to me, I will probably question every decision you've made, right? I'm going to ask, why did you do this? Why didn't you think of this, right? And the goal is to help you improve, not to make you feel bad or anything like that. But that's what we have. Okay, Is that right? That's the simple imputer. If you want the kind of the more complicated things where it takes into account other variables, you can read up on that, right? But filling in missing values, it's a common problem. Maybe you should just throw away. If like one column is missing like too many values, you might say like, all right, we're gonna throw this column out. Or I'm gonna just do a separate analysis just for the people who have these values, right? So, because maybe it's a useful thing. All right, we've already looked at this a little bit, okay? The polynomial features. Polynomial features. So when we did the cross-validation, we said we can generate, like we wanted to fit a quadratic and a cubic and a fifth-order polynomial and stuff like that. We basically use polynomial features, right? And that's from sklearn preprocessing. So here it is. Once again, you can do polynomial features degree 3, and it will just go ahead and take 1, 2, 3, 4. It'll raise it to the 0 power, the 1 power, 2nd power, and 3rd power, and so on and so forth. And so we can see our nice table of powers. And then you can fit it, all right? And as far as predicted values go, I guess I would want more values in between to get a smoother thing, but this is just kind of, you know, what we predicted. Okay. So this is a really nice thing, and this is called a feature pipeline, right? There's so on CampusWire, someone asked about pipes, and this is unrelated, but I responded to the question, and I wanted to kind of point it out here. So someone asked if Python has pipes, okay? And so, you know, is there something that looks like a pipe in R? So in R, can you guys see this? Okay, so in R, you might do something like take the data frame Kershaw and then select one column, pitch name, then group by the year, and then summarize to get the count of how many you have, and then mutate, create a frequency thing, like a relative frequency, to do n divided by the sum, and then you'll round it off, and then you'll do some kind of spread thing to kind of unstack it, okay? You can do the same thing in one line. You don't have the pipe operator, but you just kind of chain them with dots, okay? Because in Python, and especially pandas, the result of all of these operations will be either another data frame or a series, okay? And series will have their own methods, and data frames will have their own methods, okay? And so if the result of something you produced is a data frame, you can chain another method, right? And when you chain another method using the dot, that method might produce another data frame, okay? And because that results a data frame, you can chain any other method that works for a data frame, okay? If you chain a method that takes the data frame and returns a series, then you're allowed to chain any series methods, okay? And there's a lot of data frame methods, there are a lot of series methods, right? So here I've got Kershaw, which is a data frame, and this is actually not a method, it's an attribute. It's the column pitch name, okay? So this is a series. When I do Kershaw.pitchName, that's a series. And with a series, there's a lot of methods. One of them is group by. So I'm going to group by the column Kershaw.year, okay? The result of that is a series that's been grouped. And for that, I'm going to apply the method value counts. Normalize equals true. What that will do is it counts up each category that appears, counts them up, and normalize takes them from just counts and turns them into relative frequencies, okay? So it'll be basically proportions, right? So it'll say like how many four-seam fastballs did he throw, how many sliders did he throw, and it will say, you know, it'll count them up, and then it'll divide by the total, and you'll get like, you know, 60% fastballs and 40% sliders or something like that, right? Okay, so you get that. The result of this thing, value counts, is another series. It's a series of basically for each year. It's got like a multi-index series, and then I can apply the method round, okay? And so it will round that series and result in a new series, produce another series. And then I can unstack that series, and then the result of this will be a data frame, okay? And when you unstack, you have options like fill value equals 0, right? So this operation, you didn't have to do it like for this question on the exam. You didn't have to do it in one line, but it can be done in one line, right? And the more you practice with Python, the more these chaining operations become natural, okay? So it's just like everything else, the more you use a language, the more fluent you become, and you're able to like build up and make longer sentences, okay? Yeah?
So right there, the like summarize and mutate, is that all just this part right here? Like both of these types?
Yeah, summarize and mutate, that is basically value counts normalize as true.
Okay.
Yeah. Okay. And there's a ton, like you can click any of these things. So if you want to become fluent with pandas and stuff, go through this is a huge page, okay? Go through and familiarize yourself with the methods, okay? You don't have to memorize every single one, okay? But try each of these out, do an example, okay? And at least you know, like, oh, there's a thing that exists, right? Because this is because I don't remember any of these things, right? I'm always going to Google and I'm saying, pandas, how do I do this? I just know this is available, and you can do it, right? So it's linked here. So these are the methods that are available for series, and these are the methods that are available for data frames. And pretty much all of these methods will return another series or another data frame, and you can just continue chaining any of these methods together. So if it returns a data frame, you chain a data frame method. If it returns a series, you chain a series method, and you can just keep going and going and going, right? At some point, your brain starts hurting because you can't keep track of what's going on. So yeah, stop there, print out that thing, and you go, oh, okay, now that I have this, then I want to do this thing, right? So that's what you have, okay? All right, so, but anyway, we're back here, and there's something called a pipeline, a feature pipeline, and this is something that exists in scikit-learn, okay? And so here, with scikit-learn, things get a little bit more complicated. You can't just chain data frame methods and series methods, okay? But you can build up a pipeline, which is kind of similar, which says, you know, apply this function, okay? You take that result and apply another function, take that result and apply another function. So we're building up a pipeline, all right? And so here, I'm going to build a pipeline that's going to impute missing, this is a very simple pipeline, okay? We're going to impute missing values using the mean. Then we're going to transform features to quadratic things, okay? And then we're going to fit linear regression, right? And so you can imagine this could be useful for something like if you have a whole bunch of data sets, and all of the data sets are kind of in the similar format, right? Like you go to some government webpage, and they have like data sets for every year, but it's not all together. And maybe you want to do separate analyses for each of these years, right? So you're going to download the data for, you know, 2018 and download the data for 2017 and download the data for 2016. But each of these things require you to transform or do some cleaning up of the data in there, okay? And this is why we like scripts and code, okay? So some people will say like, oh, I can just open up the CSV in Excel and I can do it's simple enough. I just do, find and replace, and I'm going to clean something up like that, right? But if you have like 20 spreadsheets to go through, it can become tedious to have to open each thing up and then do find and replace every single thing on Excel. And maybe you have to delete a couple columns or something like that. When you have a script, it's really easy. You just say, you build up your kind of sequence of operations. That part might take a little bit longer. And then you just say run it on all of these files. There's actually a word in Python, and I want to call it a glob, I think. Python glob, is that right? Glob.glob. Okay, yeah. So you can tell Python to search for certain types of file names, right? So like you're downloading, I don't know, census data or something from, no, not census data, but some kind of data from some website. And they might all be similar, and you just say like, search for all of these files that fit this criteria and then run this operation on it. Okay, but anyway, back to the pipeline. So here, I'm going to do simple imputer strategy equals mean. So basically all of these things that I've done back here, right, where I've defined, where I initialize the thing, I've got imputer is simple imputer strategy mean. I've got polynomial features degree equals 3 or something like that. I'm initializing these things, and then to fit the linear regression, I do model is linear regression, right? So here I take those commands that I've used to initialize stuff, all right? And we're going to say make a pipeline out of this, okay? And we're going to just call this the model. And then I take my data x and y, and then just like everything else in Python, we do model.fit x comma y, okay? And then we can print out what it gets and its predictions. Okay, so we're probably overfitting, but it's able to predict the things perfectly. Okay. So here, this was data in 3 columns. Okay. Here now my x is just a single variable thing. Okay. And we can have it make predictions as well, okay? So we've got, basically for both of these things, it's going to impute the missing value. It's going to make fit a degree 2 polynomial, and then fit linear regression there, right? So that's a pipeline, right? This is like the simplest example. Depending on what you're doing, you might not have a use for the pipeline. Pipelines are often useful if you have several data sets, different data sets, and you want to do a similar analysis on all of them, but you don't want to like combine all the data together, right? So you just kind of take one data set, run it through the pipeline, see the results, take another data set, run it through the pipeline, and see the results. And it's as if you've written down the steps and you say, all right, this is what I want to do to this data file. I want to look at this and get the results. And if you can say, for each data set we're doing the same steps, you can build a pipeline out of it and apply it to basically all the data sets. And it really just streamlines your operations there. Okay, last thing, we can take a very quick look at looking at text features, okay? You could take an entire course on natural language processing. We're going to spend 10 minutes on it, okay? So what we're going to do is we're going to build up what's called the term frequency inverse document frequency matrix, okay? The TF-IDF matrix. I don't know if you guys have heard of this thing. TF-IDF, okay? Term frequency inverse document frequency. Okay, so here I've got, this is my sample of data, and I've kept it super simple, okay? I have 3 documents. The first document is problem of evil. The second document is evil queen. And the third document is horizon problem. You're like, these aren't documents. These are like short phrases, if even they count as that, okay? But the concept is the same, okay? The first one's just a document of 3 words. The second, and then the other ones are documents of 2 words, okay? The term frequency inverse document frequency is, we are trying to figure out how strongly one word is associated to a particular document, okay? So one way to measure how strongly a word is associated with it is we just count up how many times that word appears in a document, okay? So if a word appears many times in the document, we'd say, okay, this is strongly associated, this word is strongly associated with the document, okay? On the other hand, if it's a super common word, okay, like the word the, okay, well, first of all, the would probably just get thrown out because it's a stop word, okay? But just for example, let's say the word the shows up in this document like 100 times and you go like, oh, the word the is really strongly associated with this document, okay? So the other part of the TF-IDF is the inverse document frequency. And we say, how often does this word show up in other documents, right? And so if it's a word that shows up in many documents, we're going to say, okay, it's not that strongly associated with this first document, okay? It's just a common word, okay? And rather than trying to figure out how common, we're just going to do inverse document frequency. So, but if there's a word that appears very frequently in one document, but it shows up very rarely in other documents, that will give it a very strong TF-IDF value. It has a high term frequency and a high inverse document frequency, right? It's got a low document frequency, the inverse document frequency goes up, right? So for example, it's kind of like if you are at a restaurant and you overhear someone talk about model, okay, you will not necessarily think that person's a statistician, right? Because yes, if you are a statistician, data scientist, you talk about models a lot, but there are lots of other contexts where people talk about models, right? So if you just overhear the word model, you're not going to think, oh, there's a statistician or something, okay? However, if you're at a restaurant and you overhear someone say the word Bayesian, okay, you'd be like, oh, now I'm curious, right? Or maybe this is just me, right? So, because you're like, oh, that person's got to be either in statistics or machine learning or some kind of field, because Bayesian shows up a lot in the statistics field, but I don't know very many other disciplines other than kind of this machine learning stuff where people use the word Bayesian, right? So that's an example of how Bayesian has a high kind of term frequency inverse, subject frequency with the word subject of statistics, right? Because it shows up a lot in statistics, but not very many other things. Whereas other things like the word model or something can appear in other disciplines as well. Okay, so anyway, what we have here is we've got problem of evil, evil queen, horizon problems, right? So here, evil shows up in these two things, okay? And so it's going to be more associated with kind of these two documents, not with the third one, okay? But because it shows up in two documents, as far as how strongly is it associated with the second document, it's going to have less of an association to the second document than queen will, because queen shows up in the second document and no other document. So queen will have a strong relationship to the second document, okay? And evil will have a medium strength relationship to the second document, okay? If we look at the word evil in the first document, okay, it will show, it is, because it shows up twice, its strength of the relationship is not like the strongest, okay? And because there's 3 words here, okay, it shows, its term frequency relative to the other things, it only shows up at, as 1/3 of the things, okay? So anyway, I'm going to use sklearn feature extraction, the count vectorizer, okay? And this will just take each of these things, all right? The feature names are the columns, okay? So this first one is, there are a total of 5 unique words in our corpus of documents, okay? And so each unique word gets a column. So we have evil, all right? And that shows up in the first document and the second document. Horizon, which only shows up in the third document. Of shows up only in the first document. And then problem shows up in the first and third document, and queen only shows up in the second document. Okay, so this is the count vectorizer. And what we're going to do, so this is what we have. Okay, evil shows up in the first 2 documents and stuff like that. I'm going to just do fit transform on the TF-IDF vectorizer. Okay, and this is the result, right? So the first document was problem of evil. Okay, so we can see evil gets an association of 0.517856 with the first document index 0. Okay, whereas for the evil queen document, okay, it gets a score of 0.6, right? So it has a stronger association with the second document because the second document only has 2 words in it, and evil is one of the 2 words, whereas problem of evil, it's one of the 3 words, so it's kind of scores a little bit lower. Whereas if we look at queen, it is very strongly associated with the second document because evil queen only had 2 words, and queen is the only document, or the second document's the only document with the word queen. Okay. The word of is very strongly associated with the first document because it's the only document that has the word of in it. And its strength is at 0.68, okay? But it's not as high as queen because it has 3 words and evil queen only had 2, okay? And if we look at the horizon problem, okay? Horizon only shows up in the third document, so its score is the same as queen. Horizon is just as strongly associated with the third document as queen is associated with the second document. And then if we look at problem, it gets a score of 0.605, which is the same as the word evil associated with the second document. Problem is one of 2 words in the third document, and the third document is one of 2 documents that have the word problem in it. Okay, and so this is just a super tiny corpus, if we can even call it that. Okay, but it's useful to kind of show how strongly certain words are associated with certain documents, right? So if you were to download articles on Wikipedia about different subjects, you can say, you can take, the document on California, and you can find out how strongly is, certain words associated with California, right? Like, I don't know, what would be, like Hollywood or something, right? Like, how strongly is Hollywood associated with California as far as that document goes? And I don't know, maybe it gets a mention, maybe not, right? But you would need to kind of download all of the states, right? You would need to download all 50 states, or you need to build up a corpus to kind of get some kind of baseline of just other things against which to compare and stuff. Okay, so yeah, you can download all 50 Wikipedia articles for the different states, and then do some kind of analysis on different industries. You can look up like how often does the word technology or something, whatever show up in how strongly is it associated with things. All right, we'll end there. Next week we'll take a look at SQL. Okay, I'll try to at least get the basics on Monday, and then the Wednesday, which is, we'll see who comes. We'll talk more on SQL there. Okay, have a good weekend, you guys.